Hello, today we're going to be talking about problem 73. In this problem we are given a box of mass 36 kilograms that we are going to move horizontally with a constant force of 225 newtons. We'll move it for 21 meters. The first 11 meters of that, there will be a frictional coefficient of 0. For the final 10 meters of that, there'll be a frictional coefficient of 0.2. And the final thing we are looking for is the speed of the box at this 21 meter mark. So the first thing we'll do is make a free body diagram for the problem so that we can see how the forces relate to each other. For the first leg of the journey, we will have the force of us pulling, the gravitational force, and of course the normal force from the box resting against the surface. The second leg of the journey, we will now introduce the coefficient of friction. So we have introduced as well the frictional force as a result of that. Now I've also listed here that our x naught will be 0. All of our calculations will start with our initial placement of x as being 0 for our coordinates. This will make everything easier in the long run. Now, as mentioned, we have our pulling force of 225 newtons. To find the normal force, I just calculated the force of the gravity and took the negative of it. So that would be the 36 kilograms times 9.8 meters per second squared to get this value right here, 352.8 newtons. Now the force of the friction is just the normal force times the coefficient of friction, and that gives us a value of 70.56 newtons. Moving on, we know that we will at some point need to know the net force in the x direction for calculating the effect of friction on it later. So we have the combined force in the x direction is the force we pull with minus the frictional force, which gives us 154.44 newtons of force. And then below that, I always write down a few simple equations that I know I'm going to use during the problem to relate the variables I was given together. So here we have Newton's equation for force, the equation for velocity, and the kinematic equation for finding x. Now, starting with the first leg of the journey, we know that the acceleration is going to be equal to the force we pull with divided by its mass using Newton's work. It's going to give us a value of 6.25 meters per second squared for the acceleration. Solving our kinematic equation using our 0 for x naught and using 0 for v initial, we will find that the time for the first leg of the journey is simply equal to the square root of 2 times that distance divided by its acceleration. And that gives us a value of about 1.876 seconds. And throwing both of these values into the velocity equation, we are given that the first leg of the journey, we end with a velocity of 11.726 meters per second. Now, moving on to the second leg of the journey, we're going to take our combined force, as stated earlier, and divide that by the same mass of the box, because that doesn't change. And that gives us a new acceleration for the second leg of the journey of 4.29 meters per second squared. Now, in the second leg of the journey, our velocity initial is not equal to 0. Instead, it's equal to the velocity we found at the end of the first leg of the journey. This gives us an equation of this form for our kinematic equation. We'll move x over to the other side in order to get a quadratic equation, which we can then solve for the roots of our second time function. Because we know time is not negative, we can just focus on the positive root here. So here we have our t2 equation. This is signifying we're taking the positive root of it. And we're simply plugging in our standard coefficients for the quadratic equation into here. A little bit of simplification, and we can go ahead and get rid of our 2's underneath our accelerations, and we get this nice equation here that looks nice and clean. Taking note that our velocity equation is the acceleration times the time, and that we have an acceleration term in the bottom of our time term, we can conveniently sub this term, the time term, back into the velocity equation over here to eliminate our acceleration terms. That means that our velocity that we've gained over the second leg of the journey is going to be equal to this right here, simply the top half of our quadratic equation from above. Solving this, we get that we have added an additional 3.217 meters per second approximately to our velocity. So for our velocity final, we simply take the velocities from our two legs of our journey, add them together to get approximately 14.93 meters per second. Now, you'll notice in the problem that we are given our mass as 36.0 kilograms. This is the base level of accuracy we're given for the problem. There are values we're given with more significant figures of accuracy, but for addition, we can only rely on the single digit, so we will round that down because of the 4 here, to being only 1 decimal place. So the final answer will be 14.9 meters per second because we do not have the accuracy to carry on our decimals beyond one decimal place. So there you have it. The final velocity of our box at the 21 meters will be 14.9 meters per second.